Okay, now we come to F9, the rotor. Now the rotor, crazy amusement park thing where you spin around and then here, see the floor is actually down here. This is the floor down here. They're above the floor against the wall. And they're not falling down because there's a frictional force that's holding them up. So I like to do the rotor problem. So for the rotor problem, let's say we have, let's do a little sketch here. So this is a cutaway. So there's a person, this is going around and around like this. And then if we have our force diagram, we're going to have the friction, static friction holding us up. Got the mg pulling down. Then you have here the force, the normal force, which I'm going to put a little c down there and call it the centripetal force. Centripetal. That's what we call the force that's directed toward the center. We have circular motion like this, the centripetal force. It's also the normal force. Equals m, it's the normal force. So here, this centripetal force, we're going to eliminate it anyway, so you can call it the normal force if you want, is ma, which is mv squared over r. And then here, fs minus mg equals 0, and the auxiliary equation that gives us our friction. Looking at these two, you can see that the frictional force, actually here, you know, what's this is suggesting? This is suggesting here, if we look at this, that we immediately get an interesting equation for Fc. So let me do that. In other words, Fc is going to be mg over mu s. So you can do this different ways. The algebra, ultimately we're solving for mu s, but I just noticed that this one gives me mg, and that is that. So I very quickly can get Fc is mg over mu s. So I like doing that, and then that is, like, that's what this is. So that was my preference there, seeing that relationship. So therefore, mv squared over r is mg over mu s. The m's cancel. The mu s comes to the left, and then here I get gr over v squared. Isn't that cool? We got v squared over gr before, and now we're getting gr over v squared, and that's dimensionless, see, because the coefficient of friction is dimensionless. So there is the answer. That's it right there. That's the necessary coefficient of static friction so that you don't fall down, giving the amusement park's radius of curvature and its, say, the speed that you're going along the circle. So what we might say here is that you have to at least have that. So we could say that the equation we should report is that we want to at least be that or greater, so we don't have any accidents. So that's what we want. Notice that this result doesn't depend on the mass, which means it happens to be true for all people, regardless of their weight. But it does depend on the planet, the speed that the rotation, the rotational, the movement, the speed that you're going along the circle, and the radius of curvature. Now, I found legal things, it's good to bring the law into physics sometimes, where amusementrideInjuryLawyer.com says that the rotor, that's this thing, or the Gravitron as it's also called, circular chamber that goes around and you stick to the wall because of friction, and it says centrifugal force. We would prefer that that be centripetal. Centrifugal force, that's the force that you would appear to feel if you're inside the amusement park ride itself. And we don't like to be in a rotating frame. We like to be outside looking in. So outside looking in, the centripetal force is holding you in. But inside the frame, you feel like you're being thrown out. That's really a fictitious force that's due to being in a rotating frame. We'll talk about that more later. This says bad news. Blood can flow, all kinds of stuff can happen here that's a negative. I'll let you read this in the notes there. But it's important to consider for engineers designing these things. And they're saying here that you can get up to 3 times. In other words, you could get 3G. The acceleration could be 3G. It's like 3 times your weight. Not good. So what I was thinking that might be cool to do is design. Let's design with numbers. Let's get some numbers in now, the engineering, and see if we can see what we're dealing with. The US has to be greater or equal to GR over V squared. But remember, the acceleration is V squared over R for circular motion. So R over V squared is 1 over A. So if you put R over V squared, you get 1 over A. So this is G over A. So if the acceleration, let's say if the acceleration here is equal to 3G, like the lawyer is pointing out, then US is greater than equal to G over 3G, which is 1/3. Well, see, that's a nice 0.33. That's nice. So that's easy to obtain. You want a low coefficient of static friction, say. So that's good, but not good for the human body. And if you're old like me, you might have trouble, like pass out or something. So suppose we designed it so that A was 2G. Not as bad. Then US would have to be greater than, this would be equal to G over 2G would be 1/2, which would be 0.5. Well, see, now the coefficient of friction is getting higher. And then if we were to go for 1.5G, more gentle, that's 3/2. Notice here, if it's 3, it's 1/3. Here, if it's 2, it's 1/2. So if it's 3/2, you're going to need 2/3. You flip it. That's what we're doing there, 0.67. Now see, now we could design the rough wall, and then if someone comes in with a slick jacket, we might give them a special jacket if they had a slick shirt or something. So what I would like to do is pursue this engineering analysis a little bit more and I would like to consider, say, here is μS greater than equal to G over A. I would like to consider a case where it spins around. The time it goes around, it takes a good 3 seconds to go around, and see what kind of R I need, with the condition that I'm only going to have 1.5G. So I'm trying to design this in a way you don't get too dizzy and you don't experience high G forces. And we can do tests and put people in there to see how they do, the little research. So now to get the period, that's called the period, how long it takes to go around once. Remember that the velocity is 2 pi radius, that's your circumference, over the period. So that's how you figure that out. So when you look at the acceleration, you want this V squared over R. So this gives you your parameters, your equations to work with. So this means I got to square the v, so that's 4 pi squared r squared over t squared, but then I have 1 over r. So that simplifies to get this nice formula for the acceleration, 4 pi squared r over t squared. That's my acceleration. So if I want this to be 3/2 g, to have a more gentle g-force, then I can solve for r. R would be 3/2 g, and now I got to take the t squared up here and put the 4 pi squared down in the denominator. Bring the t squared to the right, the 4 pi squared down there, and that gives me my r. So when I plug this in, I have 3/2, I have 9.8, I have 3 seconds, and then I have 4 times pi squared. So when you do that, you get, for the r, you get 3.4 meters, all right? But I was more curious at this point to see what's going on in this one that's already built. Now, if we roughly take this to be 2 meters, then that's going to be like a little more than 6 feet. But I think, this looks a little bit more than her height or his height. So I'm going to say 2 meters for the radius. Now, what about the time it takes to go around? Well, I found a video on YouTube. Someone had made a video, and it went around 10 times in 18 seconds. So that means t is 18 seconds divided by 10. So there's the t. And now I'm going to use my formula for the acceleration. The acceleration is v squared over r. And remember, the v squared over r, we already have worked that out. We already have that equation here. So that's going to be 4 pi squared r over t squared. See, that's already been worked out over here. So we can just copy that down again. So now we're ready to plug in numbers. We have 4 pi squared, the r is 2 meters, and the time that we're putting in there is, the period is 1.8 seconds. And see, we have to square that. We'll get meters per second squared. And if I put g here to get g-force, I'll need to have g down here to cancel 9.8. So now I'm all set to get the g-force. And if I calculate that out, and it's done here for you in the notes, you get 2.5 g. See, that's pretty hefty there. That's the g-force on that ride, which we found at Luna Park, Sydney in Australia, New South Wales, Australia, courtesy of Severin, Wikipedia. Nice picture.